So, welcome everybody. It's a pleasure for me to introduce you Dr. Henri Boffin. Sorry. Well, I'm going to give you some introduction to his work. He did his PhD at the University Libre de Bruxelles in Belgium. Then he went for some postdocs in Japan and in UK. And then he came back to Belgium for a position in the Royal Observatory. After that, he, well, in the meantime, he had time to have a grade in journalism. Thanks to that, he got a position in ISO as an astronomer and press officer. He was in charge of communicating astronomy to the general public, yes. Then he went to Chile, also as ISO astronomer, as a operation staff astronomer. He was in charge of, as instrument scientist of two instruments, Force 2 and HARPS. And since 2 years ago, he came back to Europe. He's right now at ISO in Garching, and he formed part of the user support department. He is giving support to the users for helping the users with several instruments, mainly Force 2, Sphere, but also Muse and KMUS. He is right now as a several visitor. He's working with me in some Muse planetary nebula data, and he is going to be also in La Palma working with Dave Jones on these things in binary stars in planetary nebula. So, well, Henri, welcome. Thank you.
Thank you very much, Jorge, and thank you for being here. So, what I would like indeed to do is to try to convince you that we should really take into account the fact that binarity plays a very important role in understanding planetary nebula. And in fact, that most likely what we need to do is to rewrite all the textbooks. So it would have been nice to have many students here, because it's really for them that they should know that what they learn at university is most likely wrong. Okay. So this is work that I've been doing since many years now. Those are the list of my collaborators, most recent collaborators, and as you can see, a lot of them are working here at the IEC, Dave, Jorge, Romano, and Pablo, and there are some others as well. If you want a full detail of what I'm going to talk about, you can see the review paper that Dave and I wrote in Nature Astronomy last year. So, as you all know, I mean, the textbooks, they will tell you about the evolution of stars, and if you look at the evolution of a sun, for example, it is now on the main sequence. It is a nice yellow small ball, and then it's going to go up to the red giant branch, and then becoming bigger, and then going also on the AGB, a synthetic giant branch star, where it's going to lose a lot of mass, and at the end of it, it is thought that it is going to eject most of the mass, and it will then here show the white dwarf at the center of it, which is going to illuminate this envelope and going to produce a planetary nebula. So the way to work is that you need to have the slow wind from the AGB, which has been expanding, and then the white dwarf, which is going to become visible because the envelope is gone, is now going to have a much faster winds, but much lower density, and this is going to, in fact, push this material, into a spherical shell, and finally, because the star here is going to be very hot, it's going to ionize this shell, and you are going to have a planetary nebula. So in order to have that, you need, of course, to have the very right timing between the fact that the white dwarf is visible and is hot enough to ionize, and that there should be still material present from the HGB star around the star. So that's why also the lifetime of planetary nebula are thought to be between 1,000 and 10,000 years, so it's a very short time limit. So that's why planetary nebula are in fact rather rare. Even so, of course, they are rather beautiful and wonderful to watch. And so we know about 3,000 of them in the Milky Way. So if the textbooks are correct, this is indeed how a planetary nebula should look like. And this is Abel 39, and you can see that this is a very nice example where you have this shell of gas which is ionized and mostly visible only in a few nebula lines. Here is another example, even more drastic, where you can really see a very tenuous gas, but you have this shell of gas that is ionized by a central star, which must be some of them, one of them there. And so when you see that, it's all fine, and we understand it. Okay, so everything is great. The problem is that those kind of planetary nebula are very rare. Most of the planetary nebula, they are like that. They are much more beautiful, of course. They are much more intricate, a lot of shapes, many things happening there. So for us, it's much more interesting, but it is also very complicated. And it does not at all relate to the textbook example that we have seen before. And 80% of all the planetary nebula are having this kind of shape. So those are, in fact, the normal ones, not the ones that you saw in the previous slides. And so now you have to try to explain how to make these kind of things. And this is a slide I stole from Ursula. And you can see that the problem is that on the HGB, you have a star which is basically a spherical star. And then for some reason, when it became a planetary nebula, it gets those very intricate and complicated shapes. So how can that be? It's also interesting that if we manage to understand this, maybe this has also application to other kind of objects, because there are some strong morphological links with other objects. So here is, for example, a comparison between supernova 87A, which is known to have this very nice ring, and those are rings that we see also in several planetary nebula, including the necklace one. This is also these bipolar shapes that is seen in SN87A, which we see similar things in other planetary nebula. And this is the well-known Eta Carina, LBV star, that has this huge homunculus with lobes, and this is also typical of some planetary nebula like Menzel 3 in this case. So the explanation that we may find for planetary nebula may also apply for other kind of stars, so it's also very general. In fact, it seems that it's not so difficult to explain many different shapes, and people have done that already. So this is a simulation by Vincent Inke, and what he showed is that if instead of having simply a spherical star, where you have then this very hot wind from the white dwarf which is expanding to it, if you now assume that in fact there is a torus here, so some kind of very thick and dense material, then the wind is going to go preferentially in this direction and not so much in this direction here. And so you are going to have this kind of intricate shapes like that. And then the difference between those different plots is simply the orientation that you see it on the sky. So here you see it edge on, and here you see it pole on. So by seeing it at different angle, you see simply different kind of shapes. And when you look at that, well, you can see that indeed this would represent very nicely the cosmic ant, which is one example of the planetary nebula, while the same model, but seen at a different inclination, would explain the hourglass nebula. So this is all fine, but now we are back with one problem, is that we need to have an explanation for this very dense torus of material. So we need to have some reason why there is a privileged plane where there will be material which is dense enough so that indeed the material, the wind from the white dwarf, is going to go in the other directions. So what could be the reason? As always, in astronomy, if you do not understand something, the reason must be magnetic field. Okay? So that's of course what people have done here as well. This was the first thing they did. Must be magnetic field, maybe also coupled with rotation and so on. And this has been a long debate in the literature, and I don't want to go through it. I think this is the most nice reason why we can indeed simply dismiss it, and this must be the paper with the shortest abstract ever. But the title is, Can we ignore magnetic field in studies of planetary formation, shaping interaction? Abstract, yes. Okay, and I think this says it all. There has been some more, of course. I mean, the paper is, of course, going into much more details and explains it. And there are some other studies that have been done by Nordhaus and so, who basically say that indeed magnetic fields cannot be a solution because the fact that the AGB is going to expand very quickly, in fact, you are going to lose the magnetic field. So the only way that it could work is that you need to have a source of extra angular momentum that is going to keep, in fact, the rotation so that you can keep the magnetic field to be formed. So you need still, so magnetic field may play a role, but they cannot be the explanation because you still need an extra source of angular momentum. And so again, in astronomy, when it is not magnetic field, then the other explanations is generally binary stars. And because, of course, we know that many stars are binaries, and most of the interesting phenomena in astronomy are related to binary stars. And binary stars by themselves, if you have a companion, then you have, of course, a very nice source of angular momentum that could indeed provide this. But it also then provides a preferential plane, because you have, of course, the orbital plane, and this would be a preferential plane in which you could imagine to have a torus of material that is going to explain then the various shapes of those planetary nebula. So binary stars seems to be a reasonable solution to this problem. And more particularly, one aspect of binary stars, which is what we call the common envelope evolution. And there the idea is that when you have a binary system in which you have a red giant, when the red giant is evolving, it's become bigger and bigger, so at one point it's going to fill its Roche lobe. And so when filling its Roche lobe, this means that it's going to transfer material to the companion. But because it is a red giant with a very deep convective envelope, this phenomena is very unstable. And so this means the more that it gives material, the more it expands, so the more it wants to give the material. So it's just a runaway process. And so very quickly, in fact, what happens is that you will create an envelope around the two stars, and what is called a common envelope. And so the companion is in fact embedded into this big envelope, and simply by tidal drag, it is going then to spiral in. And the odd product is that you have a system of a very close binary. And so initially, the system will have orbital periods of several years, because you need the space, of course, to have an AGB star, which is a huge object. So you have an orbital period of several years. But following this common envelopes process, which is something very fast happening, you end up with a binary system, which is going to be with an orbital period below 1 day. So very close orbital periods. And then, of course, what is happening is that because of this, the shrinking of the orbit, this is in fact giving back energy to the envelope. Envelope is then going to be ejected. And because you have then the core of this AGB star, which is the white dwarf, is very hot, it is then going to ionize it, and the whole thing is going to appear as a planetary nebula. So here is a small cartoon of this process. So you can see the AGB star with the companion main sequence star. So at one point the AGB star fills the Roche lobe. It will start to accrete, but this process is very unstable, and so it forms a common envelope. And then the star inside is going to shrink. You can see that there is a professional plane, which is in fact the orbital plane where material will most likely go. And then at the end, the envelope is going to be ejected and in a bipolar form. And the outcome of this is in fact not very unlike the very nice butterfly planetary nebula. So the common envelope phase and process is a natural explanation of making a planetary nebula, and if you can have them in binary stars. In white binaries, you can also, in fact, have this kind of things, because in white binaries there you don't have this Roche lobe overflow that is going to happen. You have mass transfer by wind, but even then, you can see that there will be a professional plane, which is the orbital plane, and there will be again very strange shapes. And at the end, this envelope is going to be also ejected, and there will be a white dwarf there. So even in white binaries, you could also explain the shapes of planetary nebula. And because of that, this has led to the idea of the binary star hypothesis, which was here written up by Orsola in 2009, that planetary nebula derive from binary progenitors more easily than single progenitors. There are some even more stronger arguments, and in fact the conclusion of that is because we all know that the sun is single, there is no companion, so most likely in another 10 years people will no longer speak as the planetary nebula as the future of the sun. Okay? And this is why I said most likely we have to rewrite this book. And, but of course he said that in 2010, so we have to hurry up if we want this prediction to be right, because it's still difficult to convince people for some strange reasons. They still want the sun to become a planetary nebula, because otherwise their life will be so sad. Okay, so, but are there those close binaries? I mean, do we see them? Because it's nice to have this theory, of course, but do we see those close binaries which are the result of this common envelope inside planetary nebula? And the answer is yes, we do. We knew about 15 or so before 2008. And then in 2008, 2009, Brent Misalski and collaborator, they had this idea to cross-match, in fact, the catalog of planetary nebula with the Ogle survey. And Ogle is doing photometry of many, many stars and getting light curves. And so they could indeed identify among those a large number of planetary nebula in which clearly there was a very close binary inside, either with having eclipses, or there would be irradiations, or in some case you would have elongation from the star because it's a close binary. And in all cases, the orbital period was below 1 day or so. So clearly those are very close systems, and they are containing a white dwarf and a companion inside the planetary nebula. And because we know that the planetary nebula came from an AGB star, clearly this could not have been the original size of the system, because there is no place in a 1 day orbital period for an AGB star. You need a huge system. So clearly those systems must have gone through the common envelope phase, and those are the results. And what is then interesting is that what they found is that the closed binary fraction in planetary nebula is about 17 plus or minus 5% or so. This, however, must be a lower limit, because in most cases the way we detect these closed binaries is by what we call irradiation effects. So because we have a main sequence star and we have a white dwarf, and the white dwarf is so hot that it is irradiating one side of the main sequence star, but not the other side. So the main sequence star has a hot side and a cool side. So depending on which side you see, either the hot one or the cool one, you will see a modulation in the light curve, and this is how we can detect them. But what we have shown is that this is, of course, very dependent on the orbital period and the companion mass. And so, for example, if you have a M5 companion, you can see that this is the limit of what we can detect. So you can only detect that for the shortest periods, shorter than 2 days. So this 17% is most likely a very lower limit, because any orbital period which are longer than a few days will not be detectable from studies. So the frequency is a lower limit. So since this work from 2008 and 2009, our group has been working also very hard in order to try to find new binaries inside planetary nebula. And here just a few examples of those. What is very nice with planetary nebula is, of course, that we are doing some nice science, but also very nice images. So we really combine everything, poetry and astronomy, and we can please the eye as well as the mind. So it's really great. And now we know about 60 close binaries which are the center of planetary nebula. So clearly they are there. Okay, so this is one of the key messages that you have to retain, is that we do find close binaries in planetary nebula, and we do find a lot. We also find them where we do not expect them. This is, in fact, the planetary nebula I studied with force. You can see it is again a very nice example of a planetary nebula, because it has, and those jets are so to be precessing. And so because you see those precessing jets, the most natural explanation for that is that there is indeed a binary system, but with a very long orbital period, because you would explain, the only way to explain this precessing jet there. But we looked at it with force, and we took radial velocities of the central star, because here it is not possible to do any photometry, because the nebula is so bright that you cannot really see any signal from the central star, which is also one of the other problems we have when we do this kind of studies. So, but here we could take radial velocity of the central star, and what you can see is that when we phase them up, we can find clearly a very nice binary inside it, with an orbital period of 1.2 days. It's again a very close binary which is inside this planetary nebula. And so this must be again a common envelope system, and the jets must have been formed before, when the system was still very wide, and they were formed then. And we see another system after it has shrunk. Okay. When we look at the photometry of this object, we can, or the spectroscopy as well, we do not see any sign of irradiation. So clearly it means that most likely the companion to the white dwarf cannot be a main sequence star, because otherwise we would see this irradiation. One side will be hotter than the other side. The fact that we don't see that most likely means that the two stars in those systems are also white dwarf. So it is a double degenerate system. It is a system made of two white dwarfs. And indeed, there are also 5 orders of those double degenerate white dwarfs which are known. And when you look at all the other system, the fraction that we get from that is really very large, and for the moment it's impossible to explain by theoretical models. Also because most of the theoretical models, they can explain the formation of a double degenerate when you have a carbon white dwarf with an helium white dwarf, but here what we see all the time are 2 carbon white dwarfs. And for the moment it's really impossible to explain those. So this is again very useful to constrain theoretical models, and it will give a lot of work to the young people. One of the nice examples of this double degenerate is a work done led by Miguel Santana Garcia, and it is this object, N2428. And then, in fact, the orbital period is again very short, 4 hours, with a mass ratio of 1. And from the light curve, we can deduce that we have indeed 2 white dwarfs, and they are each so close that they are filling the Roche lobe. But what is also very interesting is that the total mass of the system is 1.8 solar masses. And because of the current orbital period, and because we know that they are losing angular momentum by gravitational waves, we can estimate that in 700 million years, the 2 objects are going to merge. And so, because they are above the Chandrasekhar mass, this is most likely the best example of a type 1a supernova progenitor. Okay, so I think you are now convinced that closed binaries exist in planetary nebula, and we have found many of them. And we have reason to believe that, in fact, the fraction is much higher than what we can see, because there is a lot of observational issues that makes it difficult for us to observe them. But does it matter? Okay? Do we see that indeed there is a link between the fact that they are binaries and the properties of the planetary nebula? And so one of the first questions we can ask is that, is there indeed a link between the binarity and the morphology? Because if our model of common envelope evolution is correct, and if indeed the reason why they have these strange shapes is because there is a privileged plane, which is the orbital plane, then there should be a correlation between the inclination of the nebula and the inclination of the binary. They should be the same, because the orbital plane should be indeed the plane in which the material is dense, and this is what explains then the shape of the nebula. And this is what Todd Ilwick and Dave Jones and others have done. So they looked at a few planetary nebula for which it was possible from kinematical modeling to determine the inclination of the nebula, and from light curve modeling we could determine the inclination of the binary. So we have both of them, and ideally we should have a correlation. And what they saw is that indeed there is a very strong correlation between the binary inclination and the nebula inclination. And if you would assume this was random, you have only 1 in a million chance to have this kind of very good alignment. So there is a very strong link between binarity and the orientation of the nebula, which seems to be, again, a very strong indication that what we see, the planetary nebula, is indeed this nebula which has been ejected by the common envelope phase. Are there some other links we can think about? The other obvious link would be the link with chemistry. And this is work which is mostly done by Jorge, and this is also why I'm here for the moment, is that in the planetary nebula, the abundances can be determined by either collisionally excited forbidden lines, which are mostly, for example, here the oxygen 3 lines, but they can also be determined from recombination lines, which are unfortunately much weaker, and so normally people use the collision lines in order to derive the abundance. But if you have deep enough spectra, you can also do the exercise using the recombination line. The big problem is that when we can do that, we find that the abundance of the element that we derive from the recombination line is much bigger, or it's bigger, on average it's bigger, than the one we derive from the collision lines. And this is what is called the abundance discrepancy factor. So there is this huge difference, and this is a well-known problem also in H2 region, where this ADF, we call it ADF, is typically around 2, and in many planetary nebula it will be above 2. But in fact we also know that in many planetary nebula it can be much, much higher. And again then the question is there a link with binarity? And so one indication there is a link with binarity is given by this object. So this is the work done by Dave. So this is NGC 677A. So using force 2, we looked at taking a slit in this direction here, so avoiding the central star. And what we can then compute was this ADF. And we can see that the ADF is typically between 20 and 40. So it's a huge difference in between the two abundance ratio that we can measure. And moreover, what we see is also that this ADF is in fact centrally peaked, so it's most important in the central part of the nebula than in the outer part of the nebula. So it looks like there are two components in this nebula. So this is already a first link that, I mean, a first hint that there could be a link between binarity and chemistry. In fact, we did a further study where we obtained spectra of several planetary nebula with force 2 at the VLT, and you can see them here with the position of the slit. And those were chosen because we knew already that those contained a closed binary inside the planetary nebula. And what we found is that for all of them, the ADF was between 13 and 80. So huge factors, I mean, really incredible numbers. So they are very extremes. And so this clearly shows that there is a very strong link between the chemistry and the binarity. And this is also shown here. So this is simply all the planetary nebula for which this ADF could be measured, taken from values in the literatures and the one we could obtain. So it's simply, they are simply ordered by their value. The blue line is the mean and the median, so it's 2.5. So we can say that whatever is below that are simple normal ones, and everything above is anormal planetary nebula. And what you can see is that, so in blue are all the ones that were already known before to be binaries, and in orange are the 8 new ones that we have studied. And you can see that basically all the ones with the binary systems are indeed with very strong ADF. And our new systems are really making this even stronger here. What we could also show is that this is here a plot between the ADF as a function of orbital period. And you can see that there is, looks like there is a kind of critical period of about 1.2 days, above which, in fact, there is no more a strong ADF. The ADF is normal. And this indeed explains those two objects here, which are binaries, but with low ADFs, but they are long period ones. So what clearly says here is that these strong ADFs are correlated to the fact that you have a very close binary inside the planetary nebula, a binary with an orbital period which must be less than 1.2 days. And as you can see here, this fraction is about half of the total number of one. So even so there may be some observational bias and so on, it still means that on the whole there could be up to 50% of closed binaries with very short periods inside planetary nebula. So it's a huge number. Is this number what we expect? This is again taken from Orsolas, and this is the distribution of orbital periods that are known for solar-like stars. And this is simply peaking at about 100,000 days, so it's a very broad Gaussian. And the systems which have an orbital period which is smaller than, let's say, 1,000, 2,000 days, those are the ones that are going to become post-common envelope systems. Okay, so all those systems that are here will become post-common envelope systems, while those ones are much wider, so they will be able to avoid the common envelope, and by a wind transfer, most likely they will widen or they will shrink, but just a little bit. Okay, so, and of course we know that for solar-like stars, the binary fraction is about 50%. So what you can see is that going from there, for this band sequence binary fraction, to what would we expect for post-AGB binaries, you would then end up with systems which went through the common envelope phase, and the other ones who did not want. And so starting from 50%, in fact, you can estimate that you would end up with about 5% of systems that would go through the common envelope phase. 5%. But of course, what we have seen is that this fraction is most likely between 20% up to 50% for very close binaries. And so we are much higher than whatever can be predicted by normal binary evolution. So this is a clear indication that planetary nebula must form preferentially in binaries. You need a binary system to form a planetary nebula in most cases. So this is now the orbital period distribution taken from the webpage from Dave. And you can see it's most of the system are very short periods, less than one day. But of course we said that, and this is very useful as well because now we can use this to compare it to theoretical model. And theoretical model of common envelope phase should be able to reproduce this kind of distribution. And for the moment they cannot do it, so there is again still work to do there. But we also saw that there could be many systems which are very wide. So what about those long period binaries? Do they exist? And the answer is yes, but of course they are much more difficult to find because if you have a long period binary, photometry will not allow you to detect them because there is no irradiation, there is no elongation and so on. So you have to rely on radial velocity monitoring. But again, if they are very wide, the orbital period is a few thousands of days, you need a lot of patience to get those orbits, and you need very good instruments because the radial velocity variation is not going to be tens of kilometers per second like for close binaries, but only a few kilometers per second, and you need very good instruments, like Hermes, for example, on La Palma. And this is also some work that Dave did with Hermes, in fact. So they could indeed confirm that two of those planetary nebula have orbital periods of about 3,000 days and eccentricity between 0.3 and 0.5. So they are very long binaries indeed. They do exist. We have some other example. This is Abel 70. And when we look at this star, in fact, from the photometry, we could see that this star is very cool and very red. And so there is no way that this can be the real central star that is ionizing the nebula. So it has to be a binary system. And indeed, when we look look at the galaxy data, so in the infrared, we can see that there is an object there which must be very hot, which is ionizing the nebula. But the object that we see here must be a companion. We cannot determine the orbital period, but again, because this companion must be a subgiant, the orbital period has to be relatively large in order to have the space for this subgiant. But more interesting is that when we took spectra of this object, so of the cool companion, what we could detect is that this is a comparison between Abel 70 and a normal subgiant star, which is in red, and you can see that Abel 70 has much stronger streamlines, much stronger biome lines, and so in fact this object is enriched in S process element. And of course this object is a subgiant, so it cannot have produced by itself this S process, but the former white dwarf was of course before that an AGB star, which could produce the S process element. So this is an indication that indeed this is a binary system, and the AGB star polluted the companion, then became a white dwarf, and the companion is now seen as a subgiant, which is enriched its S process element. So this is a clear proof that this is a binary system, and that there has been mass transfer between the two stars. This is another example, N239, which are a very nice ring-like shape, but again, as you can see, the central star there is very red. So again, it cannot be the white dwarf which is ionizing the nebula. So most likely this is a binary system as well. And when we took spectra of the central star, there again we could find that it was carbon-rich with a lot of, so the C/O ratio is much larger than 1, and it is enriched also in S process elements. So it is again a biome star, and so again it is been contaminated by the material coming from the companion, which then became this. So this also shows that in some planetary nebulae, you have also wide binaries, which are there, and those ones also show that there has been mass transfer in this system. Do we have proof that there was mass transfer in the shortest ones, where we have common envelope thing? And the answer is yes. This is the necklace, which was found by Romano in 2011, that it also contains at the center of it a binary system, a post-common envelope binary, with an orbital period of 1.16 days, and you can see it in the photometry, very nice. So we know it is a post-common system, and when we took spectra of it, we again could see that it is carbon enriched. And so again, it could not have produced the carbon by itself. So this is the first proof that even in the post-common envelope systems, there has been at one moment, mass transfer from one star to the other, and the star became enriched in carbon, and in some cases in S-process elements. So there has been mass transfer in those systems. Do I still have 5 minutes? Or yeah? Okay. So let me then finish by talking about triple, because of course we have binaries. So why stop there? I mean, we should of course also then say, but triples could also explain everything, because when you cannot explain something with a binary, you put a triple system. And triples have the advantage that if you have a third object, indeed it's more easy than to make the two stars merge, for example. And so this is what Beer and Socker said, that in order to explain the shape of some of the planetary nebula, they would need to have triple systems. And they could say that up to 20% of planetary nebula could be shaped by triples. And this may seem natural, because indeed we also know that solar-like stars are indeed also in triple systems. I mean, 50% of them are in binaries, but about 25% of them are in triple systems. So it could be that indeed. So we tried then to find some. And one best candidate was this one, SUWT2, because a paper by Exter et al. In 2010 said that in fact this, there was there in the center of this planetary nebula 2 A-type stars, which were main sequence stars, in an orbit which was with a 4.9 days. Of course, again, those main sequence stars cannot be at the origin of the nebula and cannot explain the ionization of the nebula. So this means this was their conclusion. This must be a triple system. You have a pair of A star, and there must be a white dwarf there, which is too faint and we cannot see. Even so, the morphology that is in there is more like a very nice ring that you expect more for a binary, so it's not so clear. But we look in detail into this object, and this is work I did with Dave last year, and in fact we took a lot of spectroscopy and also literature data with UVS and nucleus, and you can find here the radial velocity that we have, and this is over 1 year. And so if indeed there was a companion there, then we would have expected that the center of mass of this binary was going to show some small variation corresponding to the orbital period of the companion. But what we saw is that in fact this common velocity was in fact very stable over 1 year with very small residuals. So, and also the systematic velocity of this binary does not correspond with the velocity of the nebula. So in fact this is just a projection effect. It just happened that in front of the planetary nebula there was indeed this binary star. But of course, I mean, it's maybe not so surprising, and that's the other message you have to really bring, is that most of the stars, and especially A stars, are binaries. Okay, so if you see an A star, most likely it's going to be a binary system. So it's maybe not such a surprise. In fact, we had another surprise. with this object. So this is M32, and those are images taken at the NTT. And so you can see this is a very nice ring-like form and in a bipolar nebula. And there seems to be there a central star, which of course looks a little bit off-center, but maybe this is just a projection effect. So it can still be the central star of this nebula. So we took photometry of this central star with the entity, and bingo, what we see is that the central star of this planetary nebula is a nice photometric binary with two very nice eclipses. But then when we look at the light curve, we start to get very puzzled, because first you can see that the secondary minimum is not an orbital phase of 0.5, like it should be if the system was circular, but it is slightly shifted. So this means this is an eccentric system. But also we see two eclipses, and the two eclipses have the same depth. So this means that if this is contained, this means that we see eclipses by the two stars, so the two stars have basically the same radius. And this is of course difficult to understand if you had a white dwarf and a companion, which they should have different radius. So the orbital period we found was 1.8 day and 0.15 for the eccentricity. So if indeed those were the central star of the planetary nebula, this would be great, because it would be a very eccentric post-common envelope system, which is not necessarily foreseen by models, because the fact that you have this parallel in of the binary means that you have a lot of tidal force. So typically you expect that you have a very circular system. So it would have been great. We said, wow, this is wonderful. This is the Nature paper, okay? But then we had a bad idea to take a spectra of this object. And this is what we got. And when we took the spectrum of the object, what we can see is that we see basically the spectrum of two A stars, and with on top of it, of course, the nebula lines from the planetary nebula. So again, the conclusion is that this system is simply made of two A-type stars that are in this circular eccentric orbit, which is nothing special, and it is just, they just happen to be there in front of the planetary nebula. And when indeed we managed to get very deep image of the planetary nebula, and then we did PSF subtraction of this object, we could discover that the real central star is in fact there, and it is indeed at the center of the nebula, so it makes much more sense. But of course it is much fainter, and it is not possible to study it. But again, this shows that nature sometimes really try to be very nasty and put this very, well, on the other hand, it's very good because we were so enthusiastic and tried to do a lot of things. But of course, the disappointment coming afterwards is also very severe. So I come then to my summary, and I think you are now convinced that indeed the number of binary central star planetary nebula has dramatically increased and should be taken into account. Please remember that when you see a planetary nebula, most likely there is a binary inside it. And textbook should be rewritten, okay? So if you are writing a textbook, don't forget to include that. There is a clear link between morphology and binary, as well as between chemistry and binary nature as well of the planetary nebula. And this is of course important to understand those planetary nebula. The big advantage of those planetary nebula and the fact that we have this post-common envelope system there is that they just form, because this planetary nebula is still the envelope that has just been ejected. So we just see them after the common envelope phase. And this common envelope phase is very important to understand many astrophysical systems, and especially type 1a supernova. And for the moment, theoretical models are really unable to explain the real common envelope system. So planetary nebula are going to be very important in order to provide all the observational constraints to theory of this common envelope phase. And I have already also shown that we have proofs of accretion in several systems, depending on whether it was in wide binaries or even in closed binaries. And this is, of course, also going to be very important to test theoretical models of mass transfer in binary system. So thank you very much, and if you have questions.
Is there any question?
So if, in your opinion, most of the planetary nebula are formed in binary system, what do you expect would be the evolution of solar-type stars, or the half of the solar-type stars that are single?
Yeah, well, they will simply evolve along the post-AGB track. Simply the fact is that most likely, by the time the central star becomes hot enough to ionize the nebula will already have dissipated. So you will not form a planetary nebula because there is no material left anymore. So you simply form a white dwarf. That's all. But you don't, or if you form a planetary nebula, it will be a very faint one. So like the first examples I showed really at the beginning of the talk, where you see this very tiny bubble, this could be indeed maybe what the sun is going to make, this very faint planetary nebula. The problem is that we don't see so many of them, and that's also then a problem with the expectation from stellar evolution. So, but it could be an observational bias because, of course, they have this very faint surface brightness, and so they are very difficult to see, and you need really very deep imaging to be able to discover them. Some amateur astronomers have been able, in fact, to discover a few of those because they have the patience and they manage to get the time to observe for a very long time this region.
Yeah, and do you expect them to be more compact?
No, they are very wide, in fact. They're very wide because indeed they will have time to evolve a lot. They will not be, it's the close binaries which are the compactest one.
There was another question here.
When you have a system with two white dwarfs, like the one that you have discovered with Miguel, it is expected that in a short time, say that, will merge into one system, but meanwhile, and will produce probably a burst of gravitational waves. But even now, they should be emitting waves.
Of course, this is why.
Do you know if it is possible to detect them with present or future?
For the present, it's not possible, but with LISA, it should be possible in the future, indeed. So this is
to detect
the gravitation from two white dwarfs, which are indeed coming close to each other because they are emitting indeed gravitational waves.
And the other question is about planets. Do a large planet in short orbit around the solar type star produce some, also in theory, yes, not to produce some morphologies similar to the...
Yes, this is indeed the argument that when we talk about binary, it is binary in the very wide sense, because indeed if you have a Jupiter or some planet which is more massive than Jupiter, but closer to the star than our own Jupiter, then indeed they will also have angular momentum transfer, and they could also produce some effect. So this is the work done by Ursula and Noam Soker that show that indeed giant planets can also have an effect.
However, they will not affect, for example, the chemical composition or even the radiation details that you have seen. So there will be a way of distinguishing between a planet and a...
But the radiation comes from the white dwarf, and so they will still be irradiated, in fact. So
the planet, but you will not expect to.
No, it's, not now, but maybe with the ELT, it could be possible to do that in the future.
Do you expect similar morphologies from?
I think from the models from Noam and Ursula, yeah. And also from Jason Nordhaus, they are very similar morphologies.
What is the expected size of the torus in the center of the planetary nebula?
Well, initially it is basically the initial size of the binary system. So it will be one or two a few AUs around the binary. So it will be this kind of size, a few astronomical units. But then, of course, this torus is expanding as well, and so it will also start to dissolve.
Has it been resolved observationally, or?
There's been some attempt, but I don't. There's been, it has been done in a few cases using interferometry, where we have been able to see in some, like in the rectangle nebula, which is not really a planetary nebula, just the stage before, but there they could indeed see these stories of material.
This is a question coming from the streaming. Miguel Santander is asking this.
You should know everything.
Yeah, by WhatsApp. Well, the question is, what's your opinion about how massive should be the planetary nebula coming from a post-common envelope system relative to the planetary nebula coming from a single star?
Well, basically, I know there is a lot of controversy between this nebula mass, but I still think there is a lot of observational problems there as well, because typically the mass is still the same. It is the mass of the AGB when it will start its mass transfer. In one case, it will be the mass of the AGB, the mass of the nebula that is ejected by the nebula. In the other case, it is the mass of the AGB that is doing the Roche-Lobe overflow. So for me, the mass should be similar.
Okay.
Is there any other question? If not, we send the speaker again.
Thank you.
And just remind you that there is scientific coffee down in the library, so you can go and continue discussions there if you want.